Hello everyone, we're going to go ahead and do section 6.3, which is the rectangular coordinate system and linear equations in two variables. Now, as an overview below, we'll see the data for the unemployment rate in the US leading up to the 2020 pandemic. It's the same data, but one is easier to understand. So we have our tables there, which has the year and the percentage of unemployment. And we see all the years we see from going from 2000 all the way up to 2020. And we see all the different rates there are numerically. So if we only had these tables here, we could see the data, but it takes extra time, extra understanding to kind of figure out like what all of this data means. So a significant advantage to graphing is that we learn a lot more information faster than just looking at raw data. So we see right there then on the right, we have the unemployment rate in the United States, and it's been graphed. So all the points have been plotted and all the points have been connected with a line. And so we see the trend a lot easier. We see it goes up and then it goes down and then it goes up a lot and then it goes down kind of a lot and then it goes right back up. And so in this section, we'll go over the basics of graphing and equations of lines so we can kind of start developing graphs and whatnot. So, all right. We'll start off with the coordinate plane. So start off with the most basic part here. We say points in a plane can be identified with ordered pairs of numbers to form the coordinate plane, sometimes called the Cartesian plane. You'll most often see it be called the coordinate plane, but it can be called Cartesian plane if you ever see that. We see that the horizontal line that goes across right in the middle here, we see that one is called the horizontal line, and that's the x-axis. So the one that goes across the middle, that is the x-axis there. Then the vertical line is the one that's going up and down, and that is your y-axis. So the one that's horizontal is the x-axis, and the one that's vertical is the y-axis. So your plane is divided into 4 quadrants, and your points on the axis are not assigned to a quadrant. So if you have a point, which if we look at this picture here, we have this point, it's in red, it's at A and B. So the A is along the x-axis and the B is along the y-axis, and that creates the point P, which we see there is a red dot there. This is P and then A comma B. It just means that point P is located at A, B. And so that point, we'd say, is located in quadrant 1 because that's what the quadrant is labeled. And then it goes in a counterclockwise rotation there. So the one on the top right is 1, top left is 2, bottom left is 3, and bottom right is 4. So those are the 4 quadrants. And so point P is in quadrant 1, but if you ever had a point that was on an axis, that is not technically assigned to a quadrant. So moving forward with the coordinate plane, we say that any point on the coordinate plane can be located by a unique ordered pair of numbers, which we say A comma B. So if we look, we have the x-coordinate and the y-coordinate of the point 5 comma negative 2 right there on the right-hand side. So we have an ordered pair, that's what that is, 5 comma negative 2 with parentheses. And the first one is always the x-coordinate, and the second one is always the y-coordinate. So the first number, A in this case, is the x-coordinate of your points. And this tells us whether we move left or right from the origin. The origin is the point right smack dab in the center. It's where your 2 axes cross each other. It's usually the point 0, 0. So that is the origin. So if you have a positive x value, you'll move to the right, and if you have a negative x value, you'll move to the left. It's 2 number lines that have been crossed with each other. So with an x value number line, a horizontal number line, we know that going to the right is positive, to the left is negative, and it's the same thing for a coordinate plane. Now the second number in your ordered pair, B, is the y-coordinate of your point. That tells you to go up or down. So if B is positive, you would go up. If B is negative, you would go down. And it's always from the origin. So you're always starting at the origin, and you're either going up or you're going down. Now, the coordinates of a point specify its location on a plane. So that's why we use coordinates. It specifies a location on a plane so you know exactly where to go or where something is located. So we have a picture of a graph here with many points on it. We see we have our x and y axes, 0 is in the middle at the origin, and every line goes by 1. So if we have the point 1, comma 3, we see we're going to go to the right by 1 because it's positive 1, and then we go up by 3 because it's positive 3. We also see the point negative 2, comma 2. So negative 2 is first, that's your x value, so you would go 2 to the left, and then it's positive 2, so you would go 2 up from there to get your point. We also have the point negative 3, negative 2, so you go 3 to the left to go that negative 3, and then since the y coordinate or your b value was negative, you go down 2 for negative 2. Then we have the point here 2, comma negative 4, so you would go to the right 2, and then you would go down 4 to represent negative 4. And then lastly we have 5, comma 0. So if either your x coordinate or your y coordinate is a 0, then that means it's going to be along an axis. So for 5, comma 0, we begin with the x value, so we go 5 to the right. And then since it's 0, we don't go up or down. The point is just going to be on the axis. So if you ever have an x coordinate or a y coordinate that's 0, it's going to be located on either the x or y axis, since you didn't go left or right or up or down. All right, so as an example we'll do together, we're going to plot the point negative 3, comma 2 on the graph on the right here. So from the point negative 3, 2, we can see the x value is negative 3 and the y value is 2. The first one's always x and the second one's always y. So x value is negative 3 and y value is 2. So starting with our x value, we'll start at the origin, the spot in the center, and then with our x value being negative 3, we'll go 3 spots to the left since it's negative. So we see we have little arrows here indicating our 3 spots to the left. So that brings us to negative 3. And now we want to do the y value. Then our y value is positive 2. So from our points there at negative 3, we're going to go up 2. So you always move left or right with the x first, and then you go up or down with the y from that point of x. So we'll go up 2 to indicate our plus 2 for our y coordinate, and we place our point. That point there is now located at negative 3, comma 2. We can see there that following along our x-axis, our point is located at negative 3, and then up it's at 2. So you can always find what point, what ordered pair your point is at as well by looking along those lines. You find your x, you find your y, that's going to be the ordered pair. So let's do another one. We're going to plot the point 4, negative 4 on the graph to the right. So just like before, from the point 4, negative 4, we can see that the x value is 4 and the y value is negative 4. So since we know this, we're going to go ahead, start at the origin, and move 4 to the right for our x value. So since we start at the origin of 0, 0, 4 is positive, so we go 4 spots to the right to indicate our x coordinate of positive 4. And then since we have a negative 4 for the y coordinate, we'll go down 4 steps. So from our positive 4 on the x-axis, then we go down 4 from there, and we plot our point. That point is now located at 4, comma, negative 4. So there we go, we had a little bit of practice of plotting points. So now talking about solutions of equations. The equation form that we will be looking at is the linear equation in two variables ax plus by equals c, where x and y are both variables, and a, b, and c are all constant values. They're also called coefficients. A is a coefficient of x, and b is a coefficient of y, and c is a constant value. But they're all constant values, which is to say numbers. So examples of this would be something like 2x plus 3y equals 18, 5x minus 2y equals 0, negative 3x plus y equals negative 10, etc. So there's typically a number in front of x or y, and then it's equal to a number at the end. If there's no number in front of x or y, that technically is a 1. So it's good to remember that. Now, equations in two variables have solutions x comma y that are ordered pairs. So since you have equations with two variables, that means that you'll have a value that solves your equation for x and y. So that means your answers will always be x comma y. There's not a solution like, oh, x equals 3, y equals 5, anything like that. It's not singular, it's an ordered pair. So when it comes to equations in two variables, your answers will be something like 3 comma 2, 5 comma 0, things like that. So you'll want to keep that in mind when answering questions that are equations in two variables. So when the first coordinate of your ordered pair is substituted in for the x, and the second coordinate is substituted in for the y, your result is then called a true statement. So you can check if something is a solution by taking the values of the ordered pair, plugging it into your equation, and checking to see if it's true. So a true statement is a math operation that is undeniably correct. So something like a equals a, 5 equals 5, 1 is greater than 0, -4 is less than 4, etc. All of these things are true statements. So those all satisfy, any type of solution. So as long as it's true at the end, then that means that it's correct. If it's not true, then it means it's not correct, and you should probably redo it. So for our ordered pairs here, we have a little bit of a silly example. We say like x is a puppy, y is a kitten. Then your answer would be puppy, comma, kitten with parentheses. So the ordered pair. So if you figure out that like x is 1 and y is 2, your answer would be 1 comma 2 when it comes to solutions of equations in two variables. So that's how you can figure out solutions of equations. All right, so now we're going to do some examples together. We'll decide if the given point is a solution of the equation. So now we're given an equation and we're verifying that our point is a solution or not. So for part A, we have x plus 2y equals 13, and the point we're given is 7 comma 3. So what we're going to do to check is to plug in 7 and 3 into our equation. 7 is the x coordinate and 3 is the y coordinate. So we'll replace x with 7 and we'll replace y with 3. So that's exactly what we said. To decide if the point is a solution, we can plug in the values to check. From the point 7 comma 3, we'll have that x equals 7 and y equals 3, so we will replace them. This means that instead of x plus 2y equals 13, we're going to have 7 plus 2 times 3 equals 13. So we're replacing x and y. 7 is just 7, and 2 times 3 is 6, so we'd say 7 plus 16 is 13. We want to verify this is true. 7 plus 6 is 13, and 13 does equal 13. Since that is a true statement, we would say that 7 comma 3 is a solution. So that's how we can verify that an ordered pair is a solution of a given equation. You plug in the values of x and y into your equation and just verify that your final answer is true, meaning that it's going to be the same number equal to itself. That means that that point is a solution. So then we'll go on to B. We have negative 2x minus 5y equals negative 22, and our point is negative 1 comma 4. So just like before, to decide if the point is a solution, we can plug in the values to check. So from negative 1 comma 4, we have that x is negative 1 and y is 4. So we'll replace x and y in our equation with those numbers instead. So we'll have negative 2 times negative 1 minus 5 times 4. So we replaced x and y with their values from the ordered pair, and we're saying that this should equal negative 22. So simplifying, negative 2 times negative 1 is positive 2. Two negative numbers multiplied to each other creates positive. Then we have 5 times 4 is 20. So we have 2 minus 20 equals negative 22. Now, calculators or brains, 2 minus 20 is negative 18. And we're trying to say in this case that negative 18 is equal to negative 22, which we know is not true. So that is not a solution in that case. Negative 1 comma 4 is not a solution. Negative 18 is not equal to negative 22. Those numbers are not equal to each other. They're not the same number. So therefore, this is not a solution. So those are some examples of how you can determine if a given point is a solution of an equation. So now moving on to graphs and intercepts of equations. To graph an equation is to essentially make a drawing that represents all possible solutions of your equation. Just because you found a solution to your equation doesn't necessarily mean it's the only solution. There can be many other solutions. And the graph is the image of all possible solutions. That's what a graph is. So by graphing a bunch of points and then connecting with a line, you are representing all possible solutions of a graph. So, or all possible solutions of an equation, there we go, which is a graph. So the point A, 0, where the graph intersects the x-axis, is called the x-intercept of the graph. So we see in the image here, we have this line that goes through, and we have points that follow along with our line. We see there are points that are located there along our x-axis that follow that graph. So because we have those, we can figure out what our x-intercepts are by graphing. Now, if you don't graph, you can still find what your x-intercept is. To find A, or the x-intercept, where your x-intercept is located at the point A, 0, to find the value of A, in your equation, you'll let y equals 0, so just replace y with 0 and solve for x, and that'll give you your value of A. So you can do it algebraically or you can do it graphically, and it would be up to you. Then very similarly for y-intercepts, we say the point 0, b, where the graph intersects the y-axis, is called the y-intercept of your graph. So just like with the x-intercepts there, we have our graph and we have our y-axis here, and our graph is going through our y-axis what looks like twice, and at each of those points where it crosses the y-axis, we get a big point there, a very obvious point, and those represent your y-intercepts. So your y-intercepts are just where the graph crosses the axis, the y-axis specifically in this case. So in order to find our y-intercept, our value of b, just like how we did for our x-intercept there, you can do this algebraically, but you replace x with 0, and then you solve for your y. So the rule of thumb with finding your intercepts algebraically is that whichever one you want to find, you replace the other one with 0. So if you want to find the x-intercept, you replace y with 0. If you want to find the y-intercept, you replace x with 0. And then you solve. So we're going to do an example together. So we're going to graph 10x minus 5y is equal to 20. Then we want to know what are the x and y intercepts. So for this type of problem, like we just said, we can figure out our intercepts algebraically. But we're first going to graph our function, which will then just tell us what our x-intercepts are anyway. X and y-intercepts are. So we're going to graph this and then go ahead and figure out our x and y-intercepts from the graph. So we'll graph this together. So we'll kind of learn how to create a graph if you don't already know how to do it. So we'll do this together. So we're going to graph 10x minus 5y equals 20. And then we want to find our intercepts from that. So when it comes to graphing equations, one of the easiest ways is to create a table of values. So a table of values essentially means that you'll pick a bunch of x values and then you will calculate y values from there. Or you can do it the other way. You can choose y values and calculate x values. It's really up to you, whichever one you would like to do. So when we create our table of values, that's kind of how we're going to set this up. When it comes to creating tables of values, what I typically do is that I pick a spread of numbers that could be helpful. Usually, interesting things can typically happen around 0 or 1 or -1. And so it can be really nice to create this spread of points that will have 0 included or 1 or -1 included. So my rule of thumb that I typically do is that when I create a table of values, I like to go from -3 to +3. I usually feel like that covers a pretty good spread of numbers. That is 7 digits in that case. So 7 different values you'll use. And then you'll fill in, your y values from there. You'll solve for your y values. It usually gives you a really nice, spread of values that you can choose in that case in order to solve your problem. So all right, we'll start by creating our table of values. So we've got x We're going to make this kind of long because we're going to do some calculations with y, and then we'll have y in there. And so when we choose x, like we said, I typically like to pick numbers from -3 to 3. So we'll go -3, -2, -1, 0, 1, 2, and 3. It needs to be a little bit longer there. There you go. So we've picked values here. So now what we're going to do is that we're going to plug in our value of x into y to figure out what our y value is going to be. So we're going to plug x into our equation and then solve it for y. So that means we'll have 10 times -3 minus 5y is equal to 20. So we're going to solve this. We'll put some arrows every time we have a step here. So 10 times -3 is -30 minus 5y is equal to 20. We see here why we started to make this graph long, and I guess we'll need to make it much longer. And so we want to solve for y, so we're going to get rid of that -30 by adding it to both sides. So 20 plus 30 is going to be 50. So we'll have -5y equals 50. And then lastly, we're solving for y, so we're going to divide both sides by a -5 there. And when we divide 50 by -5, we get -10. And the last thing we're going to put over here is we're going to put ordered pair. And then we're going to draw a line across because we've completed this line now. And then we write our actual ordered pair. So we see that it definitely took us some calculations to get to our answer for y, but the ordered pair is always x comma y. So our x, like we said, was -3, and y, which we solved, was -10. So that's the actual ordered pair. That's one of our points that's going to go on our graph. So we're going to do this for every value. Let's go ahead and do it for -2. So we'll have 10 times -2 minus 5y is equal to 20. So we'll simplify. 10 times -2 is -20 minus 5y is equal to +20. We want to get rid of the -20, so we'll add 20 to both sides. 20 plus 20 is 40. And divide both sides by -5 to solve for y, which will give you -8. So when x is -2, we see y is -8. So that would be our ordered pair. All right. This is definitely a lot of numbers here. We're going to go through, we're going to do all of them. I highly suggest maybe pausing the video at this point and finding them yourself, and then checking your answers here in a second. I'm going to fill in the rest. It's going to be the same calculations, just with a different x value every time. So like I said, maybe practice this on your own, and then come back to see the answers, but we're going to write the answers all down here in about 1 second. All right, so filling in all the rest of our points here, we get our list of ordered pairs, which is plural. So we get our list of ordered pairs. So we kind of see some important parts kind of popping up here. We see that when we have x equals 0, our ordered pair becomes 0, -4. So 0, -4 is our y-intercept. So we'll put a little star here. This is our y, and that's going to run out of room for sure. So we'll put it below y-intercept. And we'll put the word int there for intercept. So since x is 0 and y is a value, that's our y-intercept. So we found one of them just by creating our table of values. And then we see another one here. When x is 2, we saw that y actually became 0. So in that case, that would make that your x-intercept. So by creating our table of values, you're actually able to find our x and y intercepts. But like we said, our question, our example here was to graph the function, and then we'll just, determine that they are the x and y intercepts once we graph. So let's go ahead and graph. When we graph our function, we want to be able to have all of the points that we've included for our ordered pairs. We want to be able to graph -3, -10, and 3, comma 2. And so we want to make sure that we have enough for all of our different points that we have. So in this example, we're only going from -3 to 3, but our lowest number is -10. Our highest number is 2. We just want to make sure we can fit everything. So let's go ahead and just make this 10 by 10 all around. And then we'll get to plot all of our points and then kind of see what that looks like. So when we graph, we want to draw our axes. So we'll have our y-axis there. You want to make it as good as possible with, your handwriting here. So I'll use some help with the Apple Pencil features here. Create some actual straight lines. There we go. So this might be a little bit wide, but we're going to go ahead. We're going to put everything on there. So we want to make sure that we have 10 notches in every direction. So that'll make it, +10, -10, +10, -10 in every direction. Like we know already, this is our x-axis and our y-axis here, so we'll make our notches. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like there's a little bit of room, so you can put like an 11th if you want. You can label them as well. When it comes to hand-drawn graphs, I usually do every other number. Every number will crowd it a lot. So we can put every other number. We can put a little 2, 4, 6, 8, 10. And then we do the same thing this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So like we said, yep, that ended up being pretty big. So we're going to erase that just a little bit or make it a little bit smaller here. It's the x-axis. So this is 2, 4, 6, 8, 10. And then we'll do the same thing going down. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That was pretty good. And then these are negative because they are beneath the origin there. So this is -2, -4, -6, -8, -10. And then we'll go to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that was too wide. So we'll fix that a little bit. There's nothing wrong with realizing that you've drawn your graph a little bit kind of off and then you just kind of rewrite everything. So you can always have that option there. So we've got -2, -4, -6, -8, and -10. So when we graph everything, we're going to follow along with our function. So starting here at the top with ordered pairs, our first ordered pair is -3, -10. So we're going to graph -3, -10 first. So here is our origin here right in the middle. We could put a little 0 or an O. Sometimes people will write an O for origin. So right there at the cross in the center, we'll start there and then we'll follow to -3 and then down, up 10, down 10, down 10, -10. So -3, -10. So we'll go 3 to the left and then we go down to 10. So our point is right there at -3, -10. Now we don't want any actual arrows on our graph like that, so we are going to erase those. But this is our point, -3, -10. By all means, you can always feel free to label your points. So that point there is -3, -10. Now our next point is -2, -8. So we're going to do the same thing. We're going to go to the left 2, then we're going to go down to -8, which is right there. Probably drew that a little too far to the side. There we go, it's a little bit better. These are hand-drawn graphs, so it is understood that they're not going to be perfect when you draw them by hand. You just want them to be accurate. So we got our point there, so we don't want those arrows anymore. And this point here, that's -2, -8. Then we're going to do the same thing for -1, -6. So we move to the left, -1. That's going to be like such a small little arrow. It's almost even hard to write. We have a -1. And then we go down to -6, which is right here. This is actually going to cover up our -6 number So you can always move it over if you would like. So we could put -6 over here. But so -1, -6 will be right about there. -1, -6. And then we're going to erase our arrows that we drew. Then our next one is 0, -4, which we do know is our y-intercept because we recognize what the ordered pair looks like, but we'll draw it on here. So it's right here. We have 0, -4. So we've got 0, -4. And then our next one is 1, -2. So now we're going to the right. So we're going this way, and then we're going down to -2 for a point right here. This is 1, -2. Erase our arrows. Then our next point is 2, 0, which is right there. It's right on the x-axis. And like we said, that is 2, 0. And then lastly, we have our last point, 3, 2. So we're going to the right by 3, and then we're going up 2, which is right here. This is 3, 2. And erase the arrows because we don't want that. So we've drawn all of these points. We've also labeled all of these points. And when it comes to drawing a graph, once you have all of your points, you want to connect all of them going from least to greatest, so from left to right. You're going to connect all of them with either what we call a smooth curve, aka, which for us is going to be a straight line. So they're all moving in a line. It's not totally perfect, as we can tell, but this should be a straight line. We see it's moving in a very linear fashion. For every one value of x, y is going up by 2. We can kind of see that pattern going there. So we go from y, for the y values, you go from -10, -8, -6, -4, -2, 0, 2. So we're skipping by 2's, but the x's are only skipping by 1. -3, -2, -1, 0, 1, 2, 3. So we have a very linear pattern. This does create a linear equation, which is a line. So we'll connect all of this with a straight line going through all of our points. We want to do this as best as we possibly can. Once again, just trying to make it as accurate as possible. I am not going to do this perfectly, but we will do our best. So we're connecting our points here in a straight line. That last one was probably a little bit off. We'll just move it over a little bit. There we go. So if that ever happens, like we say, you know, this was not perfect. I didn't have guidelines, especially in a problem like this. So just as accurate as possible. Scoot that point over a little bit. Just make it sure that it is a nice straight line. And that's mostly straight. So that's pretty good there. And like we said in our problem, we wanted to identify our x and y intercepts. We kind of did from our table, but this especially makes it so that we can recognize our x and y intercepts there and there. So we can go ahead and label this. We know our x-intercept and our y-intercept. So our x-intercept is located at this one right here. That's our x-intercept, and that's going to be at 2, 0. And our y-intercept, the point that intercepts the y-axis, is our point 0, -4. Our graph is part of our answer, but finding the x and y intercepts was our actual point of our question here, was finding the x and y intercepts in addition to graphing the function, or graphing our equation, which we've done, and we found the x and y intercept, so our problem is complete. So let's go ahead and go back on over to the lecture then. So we went ahead and did this one, so let's go ahead and move on. So now we can talk about slope. We say the slope m of a line containing the points, and that looks like x sub 1, y sub 1. So there's a 1 that's kind of a little bit small, and it's a little bit off to the right and below the x and the y. So it's like x with a little 1 and y with a little 1, but it's down below. It's not like an exponent. And so we usually say x1, y1, or x sub 1, y sub 1. So that's typically how we would say that, but writing it, you just put the little one, right below, kind of like a little hanging off your x's and your y's. Then we also have x2 and y2. So same thing as x1, y1, except now you have 2's instead of 1's. This is just to signify point 1, point 2. So you'll have 2 points that you will find the slope of between. So especially having this picture here, which is kind of in green, we see that we have this straight line, and then we have x sub 1 and y sub 1. And when those two, have the ordered pair, they create the point x sub 1, y sub 1. Then we also have x sub 2 and y sub 2, so they create the point x sub 2, y sub 2. And we see that we have this line going through, and we can find our slope by figuring out what our combination is in the distance between the x's and the distance between the y's. So in our gold box here, we have the slope, which is what we typically say is m. And m, you may have heard this before, is rise over run. So this is more signified with the change in y divided by the change in x. So the change in x and the change in y is that distance between the x values of your point and the distance between the y values of your points. So change in y is known as the rise and the change in x is known as the run. And we can even simplify this further. We know that the change is from this picture we see as, y sub 2 minus y sub 1 or x sub 2 minus x sub 1. And so we can divide those from each other. So our slope equation we know as y2 minus y1 divided by x2 minus x1. And so we know those point values from our 2 points, so we can plug those into our formula and find the slope between any 2 points. So that being said, if a line slants up going from left to right, so if you're looking at a graph of a line and it's going upwards from left to right, because that's the key there, every time you look at a graph, you're always going from left to right. You're looking from negatives to positives, from left to right. So if it's going up when you're looking left to right, then that means that your line has a positive slope. So we see down here, we say positive m, and we see it going, sloping upward here. So that has your positive slope there. Then if it slants down when you look from left to right, so remember always going from left to right, so if it's going down, then that has a negative slope. So that's your negative m value. So that means that your slope there is a negative number. So we see how the difference between a positive or a negative slope kind of changes the look of your line. Are you going up the mountain or are you going down the mountain? And that kind of tells you one way or another, kind of like what your graph should look like. So for example, what we'll do together, we're going to find the slope between the 2 points, -3, 5, and 4, -9. So since we have these 2 points here, we want to make one of them 0.1 and one of them 0.2. So we know that slope is equal to rise over run, or the change in y divided by change in x. By making -3, 5.1 and 4, -9.2, we can go ahead and attribute our values of x1, y1 and x2, y2 to our points in order to calculate rise over run, or change in y divided by change in x. So if we rewrite our points into 0.1 and 0.2, we can use the formula from our previous slide to find the slope, which was making x sub 1, y sub 1 equal -3 and 5, and x sub 2, y sub 2 equal to 4, -9. So this way we attribute our x values and our y values. So x sub 1 would be -3, y sub 1 would be 5, x sub 2 would be 4, and y sub 2 would be -9. Then our formula, which was y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1, we can put in the values that we kind of attributed. So y sub 2, like we said, was -9, and y sub 1 was 5. So y sub 2 minus y sub 1 will be -9 minus 5. Then x sub 2, which is 4, and x sub 1 is -3. X sub 2 minus x sub 1 will be 4 minus -3. So we put all of our points and all of our values into the right places for our formula. And then we just want to simplify. So negative 9 minus 5 is going to be negative 14, and 4 minus negative 3 is going to be positive 7. So negative 14 divided by 7 is going to equal negative 2. And that means our slope between these 2 points that we were given is negative 2. So that's how we can figure out the slope between any 2 points that were given to us. We can use the formula that we were given in order to figure out our slope between any 2 given points. So moving on, we can go into linear equations in slope-intercept form. So a linear equation is written as y equals mx plus b, which is also known as what's called slope-intercept form. So it's called slope-intercept form because m in y equals mx plus b is the slope, and b is your y-intercept. Your y-intercept is typically 0, comma b. It's a point. But we use the value of the y from the y-intercept in the equation. So in order to figure out the slope and or the y-intercept of an equation in standard form, which we learned earlier as ax plus by equals c, what we can do is solve our equation for y in order to get slope-intercept form. So if you have a standard equation like, let's say, 5x minus 3y equals 15, that's standard form. We can turn this into slope-intercept form by solving for y. So we'll get rid of the 5x from the left there, and then we'll do that by subtracting 5x from both sides. So once we do that, we'll be still left with negative 3y, but then we have negative 5x on the right now plus 15. Then we want to get rid of our negative 3 in front of our y. We want y to be by itself, so we'll divide everything by a negative 3. This will give us y equals, and now the negatives from 5 over 3 cancel out, but 5 over 3 is just 5 over 3, so it'll be 5 over 3x minus 5. 15 divided by negative 3 is negative 5, so that positive 15 turns into minus 5. So you can solve an equation, a standard equation for y, in order to get slope-intercept form. So that's how you can just change between one form and the other, is just by doing that. And you can always undo a slope-intercept form in order to get a standard form equation again. That is less common of a necessity, but you could if you wanted to. Then on the right of our slide here, we see a graph of a line. It looks like it's going from negative 5, comma 1 up to 5, comma 3, where we see a y-intercept at 0 and 2. So our slope-intercept form, this has been determined that the slope is 1 over 5, because that's the number in front of the x. And then we say plus 2, where 2 is the y value of our y-intercept. So by finding the slope between these 2 points, negative 5, 1 and 5, 3, we're able to figure out the slope in this case, and then we take that y value from the y-intercept and place it in for b in the equation of y equals mx plus b. So if you find the slope and you find the y-intercept, you can always create the equation of a line. You can also use the slope-intercept form to help you plot a line. On our last example that we did together in our notes, we had to find a bunch of points, we had to find all the y values, we had to plot all of the points. It was kind of long and tedious, but if it came down to knowing what the slope is and knowing our y-intercept, we can actually create that line a lot easier than having to find a bunch of points. And so this helps us graph lines. So having an equation in slope-intercept form makes drawing out lines and linear graphs so much easier. So it's usually better to have slope-intercept form when it comes to graphing linear equations. So we're going to do it all together. We're going to put the following equation into slope-intercept form, and then we're going to find the slope and the y-intercept from that, and then we're going to graph our line. So let's go ahead and go to our notes. So we have the same question here, and like we said, we're going to start with creating our slope-intercept form. So by doing that, remember we want to solve for y. So we can put a little note here to remind ourselves to create our slope-intercept form equation, we need to solve for y. So we have 2x plus 3y minus 12 equals 0. This isn't even quite standard form, it's kind of just an equation. And so we're going to do everything that we can to solve for y. So we have a constant number, we have this minus 12 that's just kind of hanging around here. We want to get rid of that. Let's send that to the right-hand side, and we'll do that by adding 12 to both sides. Negative 12 and positive 12 cancel each other out. So we get 2x plus 3y is equal to 0 plus 12, which is 12. So 2x plus 3y equals 12. So we're getting there. We want to get rid of that 2x. We want y by itself on the left. So to get rid of the 2x, we're going to subtract 2x from both sides. So this will leave us with 3y is equal to, and now for slope-intercept form, which remember slope-intercept form is y equals mx plus b. We really want that mx term first after the equal sign before the b. So when we subtract 2x, we want to go ahead, we're going to make sure that's first. So we're going to write negative 2x, and then we're going to have our plus 12. 12 is positive, so it makes it plus. If it were negative 12, it would be minus 12. But it's positive 12, so it becomes plus 12. We're going to bring this up over here to continue. So now that we have 3y is equal to negative 2x plus 12, we're going to go ahead and we're going to divide everything by 3. We want y by itself, so we want to make sure to get rid of that 3. It's currently being multiplied by y, so the only way to get rid of it is to divide. So we'll divide, and when we divide everything by 3. So we divide by 3 over here and over here. Now the 3's cancel for the y, leaving us with y, which is what we wanted. And now we have negative 2 over 3. Negative 2 over 3 doesn't really simplify, so it's going to stay that way. We're going to have negative 2 over 3, and then there's an x. And then we have plus 12 over 3, and 12 over 3 simplifies to 4. So we get y is equal to negative 2/3 x plus 4. So this is our equation in our slope-intercept form. Now we want to identify our slope and our y-intercept. Now the number in front of the x is the m, which is slope, and the number here at the end, including the operation, if it's plus it'll be positive, if it's minus it'll be negative, that'll be your y-intercept. Or the y value of your y-intercept. So when we want to identify the slope and the y-intercept, we would say the slope is m, and that's negative 2/3, the number in front of x. And our y-intercept is going to be the value of b, or that number that you are adding or subtracting at the end. But remember, it's our y-intercept. Your y-intercept is always of the form 0, b. So when we write our y-intercept, it will be 0, 12. The y-intercept is a point, so you don't want to forget that. Kind of looks like a 6. Yeah, there we go. Looks a little more like b now. So we have our slope that we found and our y-intercept. Those were pretty simple and easy from our given equation in slope-intercept form. So that's also why having it in slope-intercept form makes it easier, because you can really easily identify your slope and your y-intercept. So now that we have, I wrote 12, it's 4. There we go. 0, 4, not 12. Sorry about that. So 0, 4, we're going to make sure now when we graph our line, we're going to use this information. We're going to plot our y-intercept first because we know that that is a point guaranteed. And then what we can do, or what I like to do, is I like to make 1 point to the right of our y-intercept and 1 point to the left. Really all you need to graph a line is just 2 points, because once you have 2 points, you just draw a line in between. It's better to have more, like 3, but sometimes 7, like how we did in our first example, is kind of a lot. So I like to always have at least 3, but you only need guaranteed 2 points to create a line. But so we have our slope, we have our y-intercept, so we're going to go ahead, we're going to graph. So when we graph, we just, of course, want to make sure that we can fit everything on this graph. We know we just want to be able to have the point 0, 4, and we want to make sure there's enough room on kind of both sides of that point. A good choice is always to make a graph go by 10. So 10 up, 10 down, 10 left, 10 right. That usually makes, covers any points you could possibly want. So that's what we'll do again. I'm going to draw it out, you as well, but I won't drag you through drawing it out. All right, so we have our graph written out here and drawn out. So we're going to go through and we're going to make our 3 points. Now we know our y-intercept is at 0, 4, so we're going to make sure to go to 0, 4. So putting our point down at 0, 4, we have that y-intercept there. And then what we're going to do is we're going to use the slope to create our other 2 points. So our slope is -2 over 3. So we can really do this in 2 different ways. Since there is a negative number, you can attribute that to your rise or your run. Technically, we're going to do both. So first thing that we're going to do is that when we create our next point here, we're going to attribute that negative to the rise. So we're going to say the rise is actually -2 and our run is +3. Now, when you have a rise that's negative, it's really going to be more like a fall, right? You're going in the opposite direction. So what we'll do is we'll go down from our point, we're going to go down 2, and then we'll go to the right by 3. So that creates a point right here. And this point is located at 3, 2. There you go, 3, 2. So we can use our slope to do that. Now, we're going to do the opposite as well. So since that negative, it can go to the top or the bottom. We did the negative in the top first, and now we're going to do the negative in the bottom. So if we do the rise is 2 and the run is -3, that means we're going to go to the left 3 and up 2. So we can put a little note here. So for creating points, we can use -2 over 3 and 2 over -3 for the slope. So we created our -2 over 3 point with our slope. Now we're going to do 2 over -3. So we're going to go up 2, and then instead of to the right, we're going to go to the left. So we go up 2, and we go left 3, which looks like right around here. Erase our arrows because we don't want to have any arrows on there. And that point right there is going to be at -3, 6. So now we have 3 points, which is all we really need to draw a line. We're just going to draw a line straight through all 3 of those. Graphs typically like to take up a lot of your overall coordinate plane, so we're going to draw it out a little bit further than kind of what we did last time. We're not going to create any more points, but this straight line that goes through these 3 points, in theory, should be going through the rest of your solutions as well. So we're going to go through our points. So we're going to go down, then we're just going to kind of follow this pattern as best as we can to create a straight line. And then put a little arrow at the end to indicate that this goes on, but we don't need to. And then we'll do the same thing going backwards here. That looks pretty good. So in theory, all of our solutions should be found along these lines. And from what we just drew here, definitely looks like you've got your x-intercept right here at 5, 0. Wasn't necessarily part of our question, but it's good to recognize that, hey, that's probably the x-intercept right there at 5, 0. But there we go. Our problem wanted us to turn our equation into slope-intercept form to find the slope in the y-intercept and graph the line, which we did. We found our slope-intercept form, y equals negative 2/3 x plus 4, the slope being negative 2/3, the y-intercept being 0, 4. And here is the graph of our equation, which you can write if you would like. This is the equation of y equals 2/3 x plus 4. And there we have it. So there was that example. So let's go on ahead and go back to the lecture. So since we had that example there, we're going to move on with horizontal and vertical lines. So horizontal lines are equations of the form y equals b. So horizontal lines are just lines that have a slope of 0. It doesn't go up or down. That's what makes your line go slanted or up or down. And since there's no slope, it's flat. So your horizontal line, y equals b, would just be some number for y. There's no change in y. That means there's no slope. So for an example, you'd have like y equals 5. If you have like y equals 5, it just means that you would find 5 along your y-axis and then draw a straight line that goes just straight through 5. So if we look at our graph that's right below right there, we have our x sub 1, y sub 1, and we have an x sub 2, y sub 2. So there are 2 points there, but it's just going straight through our y-axis. We say m equals 0 because our slope is 0 there. We can even write out our slope formula and kind of try to find it. y1 is the same as what's technically y2 there because they're the same value. And since they're the same value, that's always going to end up being equal to 0. So if it's like 1 minus 1, 5 minus 5, 10 minus 10, that's all going to be 0. So you're always going to have 0 divided by a number, which is always equal to 0. Then we also have vertical lines. So vertical lines are equations of the form x equals a. So it's different. It's not y equals, it's now x equals, and it's just a number once again, just like b was just a number. They have a change in y, there's a change in the rise, but there's no change in x. And this is different than the horizontal lines. We say that this slope is undefined. So while the slope of a horizontal line, y equals b, is 0, and that's because your change in y was 0, so your formula would be 0 divided by a number. Since there's no change in x, when we have our formula for y sub 2 minus y sub 1, and what's technically x sub 2 minus x sub 1, but since they're the same x value, they're both what we can call x sub 1. That's like saying, 1 minus 1, 5 minus 5, 10 minus 10. That's always going to equal 0. And so you have some number being divided by 0, which you can't do. You cannot divide by 0. So because of that, we would say that your slope is then not defined or undefined. So that's the important difference there between horizontal and vertical lines. I mean, it's just what they look like in general and what their formulas look like, but also knowing the differences in the slope. So horizontal lines, y equals b, the slope is 0. Vertical lines, x equals a, that slope is undefined. So then we have applications of slope and average rate of change. So the grade of a road is a value that's expressed as a percentage, and it tells us how steep a road is, or in other words, the slope. So that's a real example of slope in that case. So something like a 4% grade, which would mean that the road rises or falls 4 feet for every distance of 100 feet. So 4% is the same in decimal as 0.04. And so that 4% we have as 4 divided by 100. So it means that it's going up or down 4 feet for every distance of 100 feet. So if you're ever driving, I see this a lot driving from like California and Nevada, where you have a very steep grade of about like 6%, either going up or going down. And so those are, you have to be pretty careful. But those are examples of slope. So slope is also called average rate of change for applicational problems. So we know that if you're driving on a road and you're going up and down and there's lots of hills, there is an average slope between your beginning point and your end point. It is different. It's very similar as well as the idea of speed. If you're driving a car, the speed at which you're exiting your driveway and when you're driving on the freeway are very, very different. You're not going to be driving 65 miles per hour out of your driveway, hopefully. It's very dangerous. And hopefully you won't be driving like 5 miles per hour on the freeway, because that is also very dangerous. So the average would be the average speed that you drove from beginning to end. And so when it comes to slope, we have the same idea. Your average rate of change in slope is very similar in that case. So when we find the average rate of change between any two data points, we determine the slope of the line that would pass between those 2 points. It is the average of all possible values. But when it comes to a linear equation is constant. The slope is consistent. There is no going up and down. It's always going to be the same. So because of that, in linear equations, slope and average rate of change are the same thing. We only give them different names in this case for context. So since we are only working with linear equations, slope and average rate of change are going to be the same, but we give them different names in just context. So when we talk mathematically, we talk about slope, but when we talk about real world problems, we'll probably say things like the rate or average rate of change. So for an example, we're more likely to say the water flowed from the bucket at a rate of blank, or something like the slope of the line is blank, and not vice versa. So you can even imagine the water flowed from the bucket at a slope of blank. It sounds kind of weird. And saying the rate of the line is blank. It's not quite as weird, but it's still, better to say slope and rate at different times. So it's really just the context of your word problem is going to be the difference between those two words, but they are essentially going to be the same for us. So we have our last example here. We have the U.S. Census Bureau uses demographic information to set up a poverty threshold that is used to determine how many Americans are living in poverty based on annual income. For an individual on their own, the poverty threshold was $4,190 in 1980, and it has increased at the rate of about $220 per year since then. We're going to write a linear equation that describes the poverty threshold in dollars in terms of years after 1980, and then we're going to use our equation to estimate the poverty threshold in 2020 and the year it will pass 15,000 per year. All right, so we've got quite a few things. It's kind of a long word problem. There's definitely some things we're going to have to do. So the main thing we're being asked for is that using our information that we know how much the poverty threshold was when we began and how much it's increasing, we can create our linear equation. Then we're going to use our equation to estimate the poverty threshold in the year 2020. We're treating 1980 as the origin, essentially, because we're saying that this is the poverty threshold in dollars in terms of years after 1980. So if we use the example of like 1, that's 1 year after 1980, which would make it 1981. So we're just looking at kind of years since 1980. So between 1980 and 2020, that's 40 years. So we're going to use, X as 40 in order to kind of, estimate our poverty threshold in 2020. And then finding the year it will pass 15,000 per year, we're going to need to find the year that happens, meaning we're going to have to solve for X when Y is 15,000. So that's kind of the difference between the types of questions we're being asked for. And we're going to do this all together very slowly in just 1 second here. So let's go on over to our notes so we can work on this one together. So here we have our notes here. So we're going to go through this and piece together our information. So we know we have certain info. So we can write the info that we know, if I can spell info right. So we know that the poverty threshold was 4,190 in 1980. And it also increases at a rate of 220 every year. So we see the word rate in there. That is indicative of the average rate of change or the slope. So having the rate in there, that really is the slope, which means that M is equal to 220. It's increasing by $220 every year. So now we're going to kind of piece together our variables. We were able to identify our slope by recognizing the rate. Now we can say that X is years since 1980. And Y is going to be the poverty threshold in dollars. So that's in dollars. Probably write that a little bit. There we go. So we have our poverty threshold and our years since 1980. Now, another thing that we were told is that the poverty threshold was 4,190 in 1980. 1980, remember, we're treating like the origin or like year zero in this case. Or origin. So if that's like zero, then the 4,190 is your Y value when the year is zero and X is years. So this is when X is zero. And we know that Y values when X are zero are known as the Y-intercept. So this value right here, 4,190, that's your Y-intercept or your B value. So using all that information that was just from that first paragraph, we were able to figure out kind of key information for our equation. Because remember, we want to write the linear equation there. So we're going to have our equation is going to be Y is equal to, and remember we have mx plus b, that's our linear equation, y equals mx plus b, slope-intercept form, it's the easiest one. So y is equal to m, which we said was 220, and that's x, plus b, which we said was 4,190. So we get our equation, which was part of our answer there. And now we're going to use this equation to estimate the poverty threshold in 2020 and then the year that it will pass 15,000 per year. So to estimate 2020, our year of 2020 is going to be X is equal to whatever number of years since 1980. So X is, you can use the value of your year that you were given, which in this case is 2020 for us. We can say 2020 minus 1980 because it's years since 1980. And 2020 minus 1980 is equal to 40. So 2020 has been 40 years since 1980, which means that we use X equal to 40 in our equation. So that means that we'll have Y is equal to 220 times X, which we're using for 40, plus 4,190. So we can go ahead and we can simplify this. So 220 times 40 in this case is going to be 8,800 plus 4,190. And adding those together gives us 12,990. So our question was use your equation to estimate the poverty threshold in 2020. We would now say that the poverty threshold, the poverty threshold in 2020 is $12,990. So that was our second part. So our first part was to find the equation. Our second part was to estimate the value of the poverty threshold in 2020, which was 40 years after 1980. And the third part we're being asked for is to estimate the year that the poverty threshold will pass 15,000. So if we want to know, when it will pass 15,000, the poverty threshold, just in general being 15,000, would mean that y is equal to 15,000. Because remember, y was the poverty threshold. That's what we labeled it as. So if y is the poverty threshold and we're trying to find, when it's going to pass 15, which really just means when is it finally going to equal 15, and then we're going to figure out the year kind of from there. We're going to use y equal 15,000. So we're going to go ahead and we're going to use our same equation, but we're going to replace y instead of x this time. So in our equation, we had y, which is now 15,000, is equal to 220x plus 4,190. So now we're going to go ahead and solve for x. We're trying to find the year in which this happened, and x was the year. So we're going to solve. We're going to subtract 4,190 to get rid of our constant number there. It will cancel over here. 15,000 minus 4,190 is going to be 10,810 is equal to 220x. We're trying to solve for x, so we'll get rid of the 220 by dividing. And we end up getting that x is not going to be a whole number. We're going to round this number. Or we're going to use the decimal value, and then we're going to use knowledge to round. So x is equal to, or about, 49.1. It's actually exactly equal to 49.1. There's only one decimal place. So if x is equal to 49.1, and the question is being asked to us, when is it finally going to pass 15,000 per year? What is the year that's going to happen? We see that when, the year hits 2049, that's going to be, 2029, that's the 49th year. We see that year is going to actually give us less than 15,000. So the year that it finally becomes or passes $15,000 per year, we're going to have to use kind of a little bit of, a little bit of mental gymnastics, some reasoning skills to figure this out. So if we use the year 49, and we can just kind of write this off to the side a little bit. Let's maybe choose a different color. If we write this off to the side and we use the year 49, we would say that, y is equal to 220 times 49 plus 4,190. So if we use a calculator to plug this in, we would get $14,970. So that does not reach 15,000, but the next year would be year 50. So we can try out 50 as well. So 220 times 50 plus 4,190 We can use our calculator and figure out that this would give us 15,190. So in the year of 49, or 2029 technically, because it's 40 years past 1980, that 49th year, it doesn't pass. And our value here is 49.1. So that technically tells us that's like the exact moment in time it becomes 15,000. But our question was, in what year does it pass 15,000? It doesn't pass 15,000 in the 49th year, but it does pass in the 50th year. So for a problem like this, we actually kind of had to use a little bit of reasoning for this last part. And so it does pass in the 50th year. So technically, we're kind of going to say that x equaling to 50, or this would be the year 2030, is when the poverty threshold will pass 15,000. So definitely had to use some reasoning for a question like that one, where typically, we solve for a value and then we're just like, that's it, we're done. We like plug it in and everything. But this was asking for the specific year. And so we had to kind of round in that case to our 2 years, either the 49th year or the 50th year, to kind of figure out which, would be correct. So in this case, the year 2030 or the 50th year is when the poverty threshold would actually pass 15,000, which is what our question was asking from us. So, all right, that finishes up our example there. So we'll go back to our lecture, which is finishing up here. So in summary, in section 6.3, we learned how to plot points and graph linear equations. We found slope and intercepts of linear equations, graphed horizontal, vertical linear equations in slope-intercept form, and we found linear equations that describe situations in our world. So there we go, that wrapped up section 6.3, so I'll see you in the next one.